Okay, so this is week 13 lectures. I apologize for the last minute kind of potential postponement of the lecture, and then switch back to normal time. The one dog's having some problems this morning, so we're going to get him to the vet. And we thought it might be earlier than it was, and so we're here at the regularly scheduled time. Okay, so today we're going to cover what I'll kind of refer to as matched pairs examples or average differences, and then we'll also start some linear regression. So kind of just jump into it here. So matched pairs is a little bit different than what we've done before, but it might initially sound kind of similar. So what we're going to do is it's going to be kind of two samples. So we have two samples, but instead they're coming from kind of the same population, or the samples are matched. The only difference is now there's like a before and an after period. Right? Usually, I mean, it doesn't have to be time, but somehow we're able to match these samples. Usually it's the same person, but we have a measure of like before, and then we have a measure of after. So we'll get a couple examples of this, but this is the general idea of what we're doing. So kind of the motivating examples, let's say we move a bunch of our workstation stuff around, and we look and say, okay, did productivity change, did it increase or decrease after we change this around? There's the average productivity of our 10 workers. So what we would have is the same 10 workers, so our sample is the same 10 people, but we have a measure of their before productivity and a measure of their after productivity. Okay? What we're going to do is we're going to look for the difference between that before and after productivity, and then take the average of that. Okay? So what we're going to do is go through every single person, every single observation, and find the difference between the after time period and the before time period. Right? We're then going to take the mean of that difference variable, call that d bar, and we're also going to find the variance of that difference variable. Okay? So once we find this difference variable, it's essentially just like we're looking at a sample mean with only a sample variance, right? It's instead of a sample mean, it's the sample difference, but still it's just a variable, so you can think of it as a sample mean. And we're finding the sample variance of that difference, which if it's just a variable, it's just like the sample variance of a single variable. So it's almost like going back to one population examples where we only have a sample variance. So if we only have a sample variance, then that goes back to, it doesn't matter if it's one or two populations, if we only have sample variances, we use that student t-distribution. Okay? So we said last week when we were comparing two sample means, and we only had sample variances, we had this degrees of freedom issue, which was like this crazy equation. The nice thing is when we're looking at these matched pairs examples and we're looking at the average or mean difference, it goes back to that degrees of freedom is just n minus 1. So we could do a confidence interval for it. It would basically be what we had before. So this would be the equation, but I mean, if we think about what we had prior, let me get the whiteboard here. Think about what we had before. Oh, I forgot to close this. If we think about what we had before, all right, we had sample mean plus or minus a t-value for alpha over 2 and n minus 1 multiplied by sample variance over sample size, where this guy represented the kind of standard deviation of our sample means. So the only difference is now we have a sample difference, looking up that t-value, exact same as before, and now we have that sample variance of that difference variable over the sample size. Nothing's really changed, where this kind of represents standard deviation of that sample difference. Right? Once I create that difference variable, it really is just like we have one sample mean, one population sample mean example. Okay? So really nothing a whole lot new here. If we go back to that example, we could kind of try to construct a confidence interval. So we find the before and after for every worker. We find the difference of that, and we take the average. Right? We find the average is 8.5. So a little bit more on how we would do that, just so I give a clear-cut picture here. What we would have is, let's say we have those 10 workers. So let me see if I can get this to focus a little better. So we got worker 1, 2, 3, so on and so forth. We've got before, and we have their after productivity, right? So let's say before it's 10, 8, 7, 5, 4, 9. Right? What we would do is find this difference variable, which takes the after productivity minus the before. So here it would be -2. Here it would also be -2. Sorry. Yeah, -2, -2. And then this one would be 9 minus 4, so 5. And then we would do that for every single worker. Now once we have this difference variable, we can find the mean and variance of this difference variable. Right? So that's how we're finding these numbers. Right? So we've got our mean difference and our variance on that difference variable. If we go back to this equation, I mean, we got this, our sample size is 10 workers. The only piece we have to do is look up that t-value. So here, if I've got 10 workers, and I want to do the 95% confidence interval, so 10 workers, my degrees of freedom would be 10 minus 1, or sample size minus 1, so 9. My alpha, right, so there's 5% outside my interval, so my alpha is 0.05. So I go to that t-table. Oops. Oh, don't know what that error said. We've got degrees of freedom 9. We wanted the alpha of 0.05, but divide it by 2, so 0.025. Right? So 0.025 at degrees of freedom 9, 2.262. Right? And that was because, so alpha, right, was 0.05 divided by 2 is 0.025, degrees of freedom 9. We'll find that 2.262 value. Right? So now we've got everything we need. It's just a matter of, here's my equation for the lower bound. So I plug everything in. My upper bound will be the exact same equation, except for I'm adding that margin of error. So I get this kind of confidence interval. So what we could say here is with 95% confidence, right, I know that the average change or the mean change in productivity is somewhere between 0.6 and 16. Or said differently, with 95% confidence, I can say that after we change the workstation layout, productivity on average has increased. Right? So this is an example of a matched pairs. You can imagine if I'm making a change and I want to look at did this have a positive or negative impact? Matched pairs are going to be a really common thing that we do. Right? So just like with all of our other stuff, if we can do confidence intervals, we can also do hypothesis testing. Right? So it looks almost identical to what we were doing before. It's just now I've got a mean I want to know what the true population mean difference is. I've got this assumed true value, kind of d subscript 0 here. And here's my, I've got my greater than sign, so right tail, less than sign, left tail, not equal to sign, two-tailed test. So the type of test is always based off this alternative hypothesis. So I wrote a h subscript 1 here. Like I said, you'll see that a lot on the exams, things like that. I'll always write h subscript a. Okay. So my test statistic looks almost identical to what we were doing when we had one population sample mean examples. So, oops, there you go. So, I can kind of show you the comparison, and hopefully we see like this really isn't anything really new. So, what were we doing before? Well, before we had a sample mean, we had an assumed true sample mean. We divided that by the square root of our sample variance divided by our sample size, where this represented the standard deviation of those sample means. Well, all we're doing now is the sample mean. Well, now we're looking at the sample difference, that variable that we created. We have an assumed true difference, right? And then now the variance is just the variance of that difference variable over the sample size. So that denominator represents the standard deviation of those sample differences. It's really just a slight notation change. Nothing really changed. Once the numbers are plugged in, nothing looks different. So if we go back to our example, and I want to do my test statistic here, well, I've got my average difference, I got my sample variance, I know my sample size is 10, I can plug those values in. Just like with our other two population examples, that assumed true difference, we're always going to use 0 here, okay? So I use that value of 0 kind of makes the top numerator a little bit easier. Calculate my test statistic, it's 2.44. Okay? So if I think about what levels could I reject that the assumed true difference is 0 at? Well, let's say I'm doing a two-tailed test. Right? If I'm doing a two-tailed test and I just want to know, is the difference anything other than 0? I would have to look at my alphas of 0.001, 0.05, and 0.1. But because it's a two-tailed test, if I want to look at critical values, all those get divided by 2. So I go to my student t distribution, my degrees of freedom was 9. I wanted the alphas of 0.1, 0.05, and 0.01 divided by 2. So that would become 0.05, 0.025, 0.005. So 1.83, 2.262, and 3.250. Okay? So I've got these three critical values. It's a two-tailed test, so I know that it's those values, but pairs, right? So I'm drawing this out right now in the background, but just so I can remember, make sure I get these numbers correct. So we had what? 1.83, 2.62, and the last one was 3.25. Okay. So we've got critical values. We've got pairs on each side. Okay. And the rejection region would be, for a two-tailed test, anything more extreme than these. Right? So we look back, I've got to remind myself, we found a test statistic of 2.44. So basically, where does 2.44 fall here? Will actually be about right here. So it's in the rejection region at that 10% significance level or 90% confidence level, which was the alpha of 0.1. It's not in the rejection region for the alpha of 0.05 or the 5% significance level or the 95% confidence level. Right? It just barely misses being in that rejection region. And so if it's not in the rejection region at the 5% level, it for sure isn't in the rejection region at the 1% significance level or 99% confidence level. Right? So we can only reject at the 90% level or the 90% confidence level or 10% significance level. Okay? So that was using the p-value approach, which is probably the easier one to do when we have to use the student t-distribution. I think the dot wants out, so I'm going to let them out real quick and we'll kind of... Okay. So we've done some hypothesis testing, we've done some confidence intervals. Let's work through another example. This would be something that kind of from start to finish, hypothesis testing, you could see on an exam or maybe the kind of weekly quiz this week. So this would be a good one to make sure you know how to solve. So let's say you've got this nutritionist at Starbucks. She wants to know whether or not after they posted calories on the menu, if calorie consumption decreased. Right? So she obtains transaction data for 40 cardholders for before and after. What are the null and alternative hypotheses? Well, she wants to determine whether or not calories have decreased. So that's what she wants to test for. So if they decreased, that means after minus before would be a negative value, right? Or less than 0. So that's our alternative hypothesis. If it decreased, that difference, on average, if it decreased, that difference would be less than 0. Okay? So I assume the opposite is true. So a lot of you made some mistakes on the midterm extra credit here. So if you have a less than or a greater than sign in your alternative hypothesis, you have to have the exact opposite in the null. So a lot of you put like an equal sign here. You got a less than sign and an equals. No. If you have a less than sign in the alternative hypothesis, you have to assume the opposite is true, which is that it's greater than or equal to 0 in the null. Okay? So we've got a less than sign in the alternative hypothesis, so a left-tailed test. Right? So we look this up and we find, okay, we find this average difference is 2.1, right? And the sample variance is 64. So if I want to calculate the test statistic, what would that be? Well, I've got the average difference, I got my variance, my sample size is 40. Whoops. Oh, where was it? There it is. So I've got, plug those three in, and my assumed true difference now is going to be, right, 0. Okay. Now, we can calculate this test statistic. I go ahead, plug those values in. It's 1.66. I didn't put minus 0 here, but you know, you can write in there if you wanted. Now what's interesting is I don't even have to really do the rest of my test to make a rejection decision here, because my test statistic is 1.66 and I've got a left-tailed test. The only way that I'm gonna, you know, I found a mean difference that was positive, which is what I assume to be true. That's the null. So I found evidence that supports the null, so why would I reject it? Right? If I found evidence that supports the null, I'm definitely going to fail to reject it. So kind of a weird one here. But, you know, we can imagine maybe, let's say I do a right tail test instead, and then in like the last, okay, now I've got something that, you know, goes against the null. I can find my critical values. My degrees of freedom here would be 39. I can plot the critical values, see if my test statistic's in the rejection region. Right? I could also do a confidence interval here, just to give another example of that. So I found this average difference of 2.1, and I've got the variance of 64. So the 99% confidence interval, how would I build this? Well, I've got three things I need. I know the sample size, the sample kind of mean difference, and the sample variance of that difference. The only thing left that I need, right, if I go back to my test statistic, or sorry, my confidence interval equation, so I had that, I just need to find that t-value. Right? So my degrees of freedom, my sample size is 40, degrees of freedom is that minus 1, n minus 1, or sample size minus 1. So 39, and my alpha is what? 1% outside the interval, so 0.01 is my alpha. But I have to look up, you know, alphas in both sides of my confidence interval. So instead of looking up 0.01, I look up half of that. So 0.01 divided by 2 is 0.005. So you go to this t-table, 0.005, degrees of freedom 39, 2.708, right? And because I'm just looking at, you know, I'm plugging it in my confidence interval, right? It should be relatively easy, right? Subtract that margin of error from my lower bound, add that margin of error from my upper bound. Right? Now here at the 99% level, I can't say whether or not calorie consumption went up or down, right? Because this includes positive values and negative values. In fact, it also includes 0, which means the true average difference in calorie consumption could be that it didn't change at all, right? There was no difference in before and after calorie consumption on average at the 99% level, okay? And so I always thought this was a great meme for anyone who remembers the cult classic Napoleon Dynamite. The barista at Starbucks asked me for my name today, so I guess you could say things are getting pretty serious. I should have done that in the Kip voice, but you can imagine. Okay, so I do want to do an example of this in Excel. I will not post this as a separate video, so this will be kind of self-contained in the matched pairs. Right? So what we want to do is say, okay, I've got, you know, everything I've kind of set this up, and the examples that I'll give you like on the exam will always be before and after time periods. But we can match on other things as well. So I'm going to do an example where we look at the same counties, and instead of before and after time periods, we compare two different demographic groups. So male and female suicide rates here, what I'm going to compare. Right? So we'll come back to this slide. But if we go back to the Excel file we were using last week, two population hypothesis testing blank, so that's in the in-class data folder. We worked with these other four worksheets, but we didn't deal with this suicide data. So let me zoom in here. So how would I kind of do match pairs in practice if I just had some data? So here I've got all, you know, these different counties in different time periods across all the different states. Okay? So I've got kind of, and I don't have every single county here, otherwise it'd be population data. I have the sample counties. So here I've got kind of my you know, male suicide rate and my female suicide rate. I could do kind of the difference in suicides. In fact, I'll use those just to kind of, because I think it makes a little more sense. It's easier to interpret. All the differences, the rates, like get divided by the population, so it kind of factors in. If a county had, you know, a higher male population, then you might expect, even if the rates were the same, they would have kind of higher male suicides. But let's just do the difference because the number's a little bit easier to think about. So I'll do the difference in male and female suicides. So I'm going to take male suicides in each county and subtract the female suicides. Okay. Once I've done that, right, if I go over here and it turns this black cross, if I double left click, copies it down for every observation. So I now have this difference variable, right, which is the difference in male and female suicides. Well, once I have this difference variable, how do I find the mean difference and the sample variance of that difference? Well, that's just our average function. We should be pretty familiar with that. Select the first cell, Control Shift, or on a Mac, Command Shift, hit the down arrow. For the variance, you can use var.s, right? Select that column of data again. Sample size, this is where we're using that count function. Select the entire variable, Control Shift, or on a Mac, Command Shift, down arrow. And now I've got the three things I need to come up with my test statistic, right? Because if I have this difference, if I just want to know, let's say, well, what do I have this set up? We want to test for whether or not the difference in males, yeah, is it not zero, right? So is it anything other than zero? So we have a two-tailed test where, because our alternative hypothesis is going to be, is this average difference not equal to zero? Well, so we'll assume it is equal to zero. We've got a two-tailed test, right? So if we have a two-tailed test, we assume that difference is zero, right? And actually, before I do this, I'm going to set something up here. Let's say the hypothesized true value, we're using zero here, right? Okay. So I'm going to set up that test statistic where I take the sample mean difference I found, subtract the assumed true difference, which is zero, divide it by the square root of my sample variance divided by my sample size. Okay. So I've just used Excel to be a calculator for me here to do that test statistic. Okay. So I hit enter. This test statistic is huge, so hopefully we can imagine, like hopefully it's starting to kind of we're getting familiarized. When I see a test statistic this large, right, the p-value is the probability I saw something that large or even larger, right? And so the area to the right of a test statistic like 4 would be approximately 0. So the area to the right of a test statistic of 40 is going to be really, really close to 0. So how can I find that though? Well, we've got this student t distribution we're using, right? I don't want to use t.inv, sorry, t.dist. Here's my test statistic. My degrees of freedom is the sample size minus 1. And then when I tell it to be cumulative, this is going to return me the area to the left of my test statistic. Well, I just said, right, if I've got this positive test statistic, I want the area to the right. So I would have to then subtract whatever the area to the left is from 1. Right? Now see, it's approximately 0 here. And I'm going to give you a quick visual here. Right, what we're doing to find the p-value is we're taking our test statistic. Our test statistic was 39. We want the area to the right of it. Well, that t.dist function told us the area to the left. So if we know the area to the left, oops, we would just do 1 minus that to get the area to the right. Now for a two-tailed test, one thing I forgot to do is what? I also have it was equally as likely I could have seen something 39 standard deviations below. So whatever area I find for this tail, I have to multiply it by 2. So when I go back to Excel, what I deleted it, there we go. So that'll give me the area that's in the right tail, but the other thing I have to then do is multiply it by 2. Now it's pretty much 0 because this test statistic is so large, right? But what I'll show you, and I'll play around with this in just a second, but we could have also used that t.dist.2t. So that's telling I have two tails. So take this test statistic, this degrees of freedom, and it finds it's pretty much 0 here. This gets a little bit more, that it kind of changes the initial formatting. The formatting is a little bit different on t.dist than it is on t.dist2t. So this kind of tells you if you took 1.1 and moved the decimal point 231 spots to the left. So this is basically 0 as well. And we'll see these give us the same value here in just a second, once it's kind of formatting isn't play a role. So here, what I started out was that I was testing for whether or not there was a difference in suicides, or I assumed the difference was 0 between males and females. Well, I found very strong evidence, right? I have a p-value of 0, so it only rejects if the p-value is less than alpha, right? Well, with p-values of 0, I can reject at any alpha, right? So I can reject at the 90, the 95, and the 99% confidence level. But what if I said, okay, I want to know whether or not just are they different from 0, is that difference kind of anything greater than or less than kind of 20, right? So I'll hit enter there. I still have a test statistic of 21. These are still essentially 0. Is that difference in male and female suicides on average across counties greater than 40? Okay, now I start to get a little bit smaller p-value, but it's still what? Let's move this decimal 0.5 spot, so 0.00004. What about 45? Okay, now I start to get a test statistic where the p-value is kind of flip the test statistic here because it was greater than the mean I found. So let's say I do 44. Well, now I'm getting a really low test statistic. That p-value starts to get really high. I can't reject at any level. So maybe, let's say I'm more interested in like a 42. Okay, here's an interesting one, because now, can I say that the true average difference in male and female suicides is anything different than 42, right? Or here, I could change this to a one-tailed test, but we're doing a two-tailed test still, so I won't say greater than 42, but just different than 42. We found evidence that it is different than 42, and what level of confidence can I say that it's different than 42? Well, my p-value is less than the alpha of 0.1 and 0.05, right? 0.02 is less than both of these. So you can think about, I would reject at the 10 and 5% significance levels, or reject with 90 and 95% confidence. But for an alpha of 0.01, my p-value is actually greater than that. It's not less than that, so I would fail to reject at the 99% confidence level, or I would fail to reject at the 1% significance level. Okay? And I'll put these in here so when I post this later, you can kind of remind you of this. Oh, well, I don't know why I went there. Here we go. So we've got the 10, 5, and 1% significance levels, which correspond to 90, 95, and 99% confidence levels. Okay, so that's all good and well. We talked about one thing last class, or last Excel video, that we could use a shortcut. So I don't have to calculate the test statistic and then use the t.dist. I can actually use a shortcut. So when we're doing it with two sample means, we use this t.test. Now before we selected the two variables we wanted to find the mean of. When we're doing a matched pair example, we select the two variables that we want to find the difference between, right? The average difference. So male and female suicides here. So the very first column, whoops, if I can scroll this over. Here's male suicide, so we'll select that row of data. Put a comma. I'm going to go back up to the top so you can see what we're doing here. The next thing I do is select the female suicide variable. So here, column I, select that. Put another comma. So I've selected the two variables I want to take the difference of. We said we were doing a two-tailed test. And now, last class, we were using this option 3, which is we were comparing two means with different sample variances, unequal variances. Well, now we're not comparing two sample means, we're finding the mean of the difference between two variables. So that's a matched paired example, matched pairs. Right? So now we'll put a comma, a 1 here. That will now treat this as a matched pair example. So what it will do behind the scenes is it'll calculate this difference variable m for you. It'll then find the mean, the variance, and the sample size behind the scenes, calculate a test statistic, find the p-value for a two-tailed test, and spit it back out at you. Right? So we hit enter there, and sure enough, we get, if we have the hypothesized true value of 0, we get the same result. Right? It's basically p-value of 0. Okay? Now, one issue here is, if I do want to do any other value than 0, like the 42, notice there's no option for me to set that. It's always defaults to 0. So this is where we said the t.test is helpful, because quite often we do have a null or alternate hypothesis for a matched pairs or a difference in sample means. The usual assumed true hypothesis could be it's 0, equal to, greater than, or less than 0. But if we want to use any other value than 0, that kind of shortcut doesn't work, and we have to calculate the test statistic and kind of find the p-value using this t.dist function. Okay? All right, so that should wrap up kind of match pairs. So I'm going to set this as a separate video. So I'm going to stop the recording here, and I'll post a second one, which is the initial start of kind of our linear regression discussion.